Hi, I'm Jim Burnham. Welcome to Thermochemistry. This chapter focuses on heat and chemical change. Our last chapter we talked about the properties of solids and liquids and gases, and that was probably a more intuitive chapter. This chapter is going to explain the energy flow that happens during chemical changes, and we're going to quantify that. We're going to perform mathematical expressions. So this chapter is going to be a little bit more abstract and perhaps a little bit more challenging. The first section, we're going to talk about the flow of heat energy. So, as you know, some things give off heat, fires. Some things absorb heat, ice. Thermochemistry studies the heat changes that accompany chemical reactions. So it's going to examine the heat effects of various chemical and physical processes. But in order to do that, we first have to get a handle on what energy means and what energy transformations mean. So, buying gasoline. Buying gas, when you do that, you're buying the potential energy that gasoline contains. And this potential energy in the form of chemical bonds does work. It propels the car. So this chemical potential energy is a property of the chemical structure of the gasoline molecules. And when those molecules are broken apart, as in the case of combustion, then energy is released and it can do work. Well, what is work? Work is force used to move an object. Okay, let's get a handle on energy because we've talked a lot about energy. So what is energy? Well, as we say, it's the capacity for doing work or supplying heat. Because, unlike matter, energy is weightless and odorless and tasteless. And remember, the universe, the physical universe, material universe is made up of matter and energy. And matter we've talked about, right? Matter is that which has mass and we can weigh it, and it comes in, around 100 different elemental varieties. But energy is different, right? Energy is not a thing. It doesn't have mass. It doesn't take up space, but it can still move matter. So we can define energy provisionally as the ability to make things move. Matter is a thing. Energy is the stuff that moves things. And examples are light and heat and sound and motion. Last chapter we talked about kinetic energy, the energy of movement. Electricity, those are all forms of energy. So just a quick division here. Matter, it's the stuff that comes in, like we studied in chapter 10, solids, liquids, and gases. It involves living things, non-living things, but energy is the stuff that makes stuff happen. It moves stuff. It comes in the form of light and electricity and heat and electromagnetic and potential and kinetic. And it was an example we talked about kinetic last time. We're going to talk about potential energy, especially in chemical bonds, like the gasoline example. So here's some other forms of energy. Nuclear energy, light energy, magnetic energy, chemical energy, thermal energy, kinetic energy, potential energy. So this is a key concept. Energy can only be detected by its effects, by the stuff it makes happen. We can't detect it directly. This is a little weird, but that's just the way it is. Different substances store different amounts of energy. So the fossil fuel industry, for example, the fossil fuels are very efficient energy storage systems. So when we burn fossil fuels, we're burning stored, essentially solar energy. The kinds and arrangement of those atoms determine the amount of energy that is stored in a particular compound. Now, one special kind of energy is heat. And heat is energy that spontaneously flows or transfers from warmer objects to cooler objects. So you don't have to do anything to make this happen. If they're close enough, where there's something that can transfer this, some medium, whether it's air or water, or they're simply in physical contact, the warmer object will transfer heat to the cooler object, and the cooler object will absorb that heat. Now, heat, again, like other energy forms, cannot be detected by the senses or by instruments. You say, well, wait a minute, what about a thermometer? Well, a thermometer can only detect a change caused by heat, and that change is a rise in the temperature of stuff. So heat causes a rising temperature, and that we can detect. You can detect that with your hand, right? Your senses, your skin can detect a rise in temperature, but that's an effective heat. It's not heat, which is again a little counterintuitive. Heat always flows from a warmer object to a cooler object. And if two objects remain in contact, the heat will flow from the warmer to the cooler until the temperature of both is the same. And that is known as thermal equilibrium. So a hot object will radiate heat outward, and a cool object at room temperature, for example, will absorb heat from the room. All right, so yeah, thermal equilibrium is when both objects are the same temperature. So if you leave the coffee out long enough, eventually it'll radiate enough heat out that the coffee and the room will be the same temperature. If you leave the popsicle out long enough, eventually it will absorb enough heat from the room that the room and the popsicle are the same temperature, and you're going to have a puddle of sugar. So again, just talking about thermal equilibrium. You leave them in contact, heat flows from the hotter to the cooler until both are the same temp. Heat can transfer or move in three ways: conduction, convection, and radiation. And the easiest way to illustrate this is probably with something like this. So with a fire, the heat that you can feel, even when you're on to the side of the fire, that is radiant heat. Convection is the heat that is absorbed above a hot object. So this fire is convecting hot air, and that hot air is then convecting water, and the hotter water is moving and then heating up the water, the cooler water above it. And then there's conduction. As you hold the handle, you can feel the heat moving up the metal to your hand. So those are the three ways that heat moves or is transferred. Now, when you talk about two important concepts that are going to be with us again, for the rest of our chemical adventure, exothermic and endothermic processes. Endothermic simply means that it is going to absorb heat. So endo means it's going to come into. Exo, like the word exit suggests, it's going to flow out of. So if you take a piece of ice, you let it sit at room temperature, it's cooler than its surroundings, but it's going to absorb heat from its surroundings and take that in. That's an endothermic, a heat absorbing process. But a burning match or a burning log or something is going to release heat. It's hotter than the surroundings, and it's going to release heat into the surroundings. That heat is going to exit this small system and it's going to go into the larger surrounding. Essentially, all chemical reactions and changes in physical state involve either the release or the absorption of heat. So we need a term, and that's what this is. Exothermic, heat flowing out of a reaction. Endothermic, heat being absorbed by a reaction. Now the system is the part of the universe that we're focusing on. So in this picture here, or even this picture back here, the system is the thing that we're looking at. The ice cube, or the burning match, or the burning log, or the reaction inside the test tube or the beaker. That's the part of the universe we're focusing on. And the surroundings is everything else in the universe. And thermochemistry basically examines the heat flow either from the system, if it's hotter, to the cooler surroundings, or from the cooler surrounding, or sorry, from the warmer surroundings into the cooler system. Again, system is what we're focusing on. Surroundings is everything else. But generally, we don't consider even the surroundings as the whole universe. You know, if we're looking at a piece of ice, the system is sitting on a table, melting, we would consider the room essentially to be the sufficient surroundings to account for that heat flow. Heat flow follows, just like all the other things in chemistry, the law of conservation. Remember, there's a law of conservation of matter, but there's also a law of conservation of energy. Just like matter, energy cannot be created or destroyed, but it can be converted from one form to another. Here's the essential point. The energy you start with is the energy you must end with. It doesn't disappear. You have to account for it. And remember, we always calculate heat from the point of view of the system. So from the point of view of the system, if the system is a piece of ice, we would say that ice is pulling in heat. It's absorbing heat. It's endothermic. The fire, the match, the candle, whatever, it is giving off heat. So from the point of view of the flame, it's giving off heat into the surroundings. Again, just another way of looking at this. We're going to introduce a symbol very soon called H. And H is a symbol for heat content. And a fancy word for that is enthalpy. But the H is nice because just remember it stands for heat content. And the delta here is going to be a change in heat content. So here is an exothermic process. And here is cooling. It's an endothermic process. Heat capacity and specific heat. What does it mean to burn calories? Okay. We're always, people are into fitness are always talking about how to burn calories, different ways to burn calories. How many calories did you burn doing this or that exercise? So during physical activity, our bodies generate heat, and we measure this heat in something called calories. So calorie is a very specific thing. It's defined as the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay? The heat to raise 1 gram of water by 1 degree Celsius. That's a calorie. But a food calorie is actually 1,000 of these calories. So it's important to remember that. When a candy bar says, "Oh, it's 150 calories," it's not just going to raise 150 grams of water by 1 degree. It can raise 150,000 grams of water by 1 degree. So a food calorie is known as a kilocalorie. It's 1,000 calories. And we write it a little differently. We typically write calories, food calories, with a capital C. And we write the regular calorie with a lowercase c. And this lowercase c is related to the SI unit of heat and energy known as the joule. Specifically, it takes 4.184 joules to equal 1 calorie. So that is a very important conversion factor that you might want to commit to memory. Joules to calories, you will use this. If you want to convert food calories, here's a food calorie. 1 food calorie equals 1,000 chemical calories. Remember, a calorie is the energy of raising 1 gram of water 1 degree Celsius. So the amount of heat needed to increase the temperature of any object exactly 1 degree Celsius, not just water, is known as the heat capacity of that object. So we can calculate, or we can figure out the heat capacity of any object, and different objects will have different heat capacities. Certain things are easier to warm up than others. Certain things absorb heat more quickly and others resist it, like water. Water, it takes a lot of energy to heat up water. Now, heat capacity depends on mass as well as upon chemical composition. Obviously, a larger object, here's a giant piece of iron, it's going to take a lot more energy to heat this big piece of iron up than it would to heat up this little piece of iron in this nail. So obviously mass is an important consideration when we talk about heat capacity. This can absorb a lot more heat, has a much greater capacity for heat absorption. A glass of water has a lot more heat absorbing capacity than a drop of water. And of course the ocean would have even more. But what we want to do is we want to compare different substances with the same mass. And even there, they may have different heat capacities. What is hotter to touch on a sunny day? A 20 kilogram puddle of water or a 20 kilogram iron sewer cover? Imagine both of these are out on a hot summer day, being baked by the sun, and you touch one of these with your foot, say, or your bare foot. Which is going to be hotter? Well, you know, the metal is going to be a lot hotter than the water, right? Why is the cement around a swimming pool always hotter than the water in the swimming pool? Because they absorb heat differently. And the water can absorb a lot more heat with a smaller change of temperature than something like metal. So we would say that water has a larger specific heat capacity, gram per gram or kilogram per kilogram, than does metal. Both absorb the same radiant energy from the sun, but the water's temperature changes less than the iron's because its specific heat is greater. So now we're going to define the specific heat capacity is the amount of heat it takes to raise 1 gram of any substance 1 degree Celsius. So we define a calorie as the amount it takes to raise a gram of water 1 degree. But specific heat capacity is the amount of raising 1 gram of any substance 1 degree Celsius. Here are some specific heat capacities of some common materials. If you'll notice, here's water by comparison, okay, 1 calorie per gram. And in joules, that's 4.183 or 4.19. Almost everything else, if you'll notice, is less than water. Ethanol, that's alcohol, that's less. Water is less. And now look at metals, aluminum. It's only 20%. It absorbs heat, or it changes heat 5 times faster than water will. And iron, it heats up 9 times faster, essentially. Copper, 10 times faster. So these materials with a low heat capacity will heat up much more quickly given the same amount of heat input. So we can define specific heat mathematically as this: the amount of energy it can absorb per mass per change of temperature. Generally, it's the amount of energy that 1 gram, that it takes to raise 1 gram 1 degree Celsius. That's our equation for specific heat, Q over m delta T. Now, we can rearrange this, and we can put the Q over on this side and say that the change of energy is equal to the mass times the specific heat capacity times the change in temperature. And this is probably the most useful form of this. And this, again, this is the same as this. We're just rearranging it to put the energy over here, and we're going to put the specific heat capacity over here on this side. And I like to think of this as Q equals MCAT. It's not an A, but it looks kind of like an A. So Q equals MCAT. That's a great way to remember this formula. Now, if you have to solve for C, you can just rearrange it, and that's C, specific heat, and you can put that back over here, and you'll solve if you have these other variables. Another way of writing the same formula is delta H. Delta H is the change in heat, and that's the same as the energy that absorbed. When something absorbs energy, it's going to change in heat content, and so we can calculate that. So this is the same thing. Delta H equals MCAT is the same as energy equals MCAT. All right, let's look at our first sample problem. We have a piece of copper with this mass. It increases from 25 degrees to 48 degrees when the metal absorbs this many joules of heat. What is the specific heat of copper? So, ACE, right? Analyze, calculate, evaluate. What are our knowns? Well, we know the mass of the copper. We know the delta T. It's the difference between the final temperature and the initial temperature. 48 minus 25 is a 23-degree change in temperature. We know our energy is 849 joules. So we want to find out our specific heat of the copper. So we're going to use the formula, C equals Q m delta T, to calculate this. And yeah, our units here are going to be joules per gram per degree Celsius. So this is our formula that we need. We have everything here except C, and so we'll just plug it into the formula and solve. So we just plug up what we have. So yeah, 849 divided by our mass divided by our temperature change. We crunch the numbers and we keep track of our units, right? Joules per gram per degree Celsius. Our answer has the units we expect. Therefore, we're confident that we did it right. Does it make sense? Well, remember, water has a specific heat capacity of 4 joules per gram per degree. And this has basically less than a tenth of that. Does that make sense? Well, yes. Especially when we remember metals have very low specific heats, generally around a tenth of that of water. So this calculated value makes sense. All right. This next section, we're talking about measuring and expressing heat changes. So certain things give off heat, like a burning match. But remember, heat can't be detected by the senses or by instruments. So how exactly do we measure how much heat is released from a burning match? Well, we use something called calorimetry. Calorimetry is a way, it's a technique of measuring the absorbed heat. Now, energy changes occur in many different systems. You can have mechanical energy being produced by a clock. You can have here, volcanic energy. You can have, kinetic energy, the movement of the planets, for example. So each of these systems has energy. The heat that is released or absorbed during many chemical reactions can be measured by this branch of chemistry known as calorimetry. And it is the precise measuring of a heat change for a chemical or physical process. It works like this. The heat released by the system, in this case the match, is going to be equal to the heat absorbed by the surroundings. In the case of that picture, the room. But if we locate the system in a different way, in a more contained surroundings, then we can actually calculate, we can measure and then calculate the heat absorbed. And that will let us know how much heat was lost. What law describes this relationship? The law of conservation of energy. Whatever energy is lost by the system must be gained by the surroundings. So this is a device, the calorimeter, to measure the absorption or release of heat in a chemical reaction. The most simple kind is known as a foam cup calorimeter. And this usually consists of a foam cup nestled in another foam cup because foam is a great natural insulator. So not too much of the heat is going to be lost to the room. Right? We want to keep the heat absorbed in a place where we can measure it. And we put a thermometer in, and so this happens. So we will have a reaction happening in water here. We'll measure the initial temperature of the water, do the reaction, then measure the final temperature of the water, and the thermometer will tell us the temperature change, and from that we can calculate the energy through our energy equals MCAT. So for systems at a constant pressure, which most things are, the heat content is known as a property called enthalpy. and we abbreviate that with H. And that's nice. This H stands for heat content. So if you ever forget what enthalpy is, remember enthalpy equals H equals heat content. And so when we talk about a heat change, we're talking about an enthalpy change, and we abbreviate that delta H. Get used to this term delta H because we're going to see it all the time. It just means a change in heat content, or an enthalpy change, a change in enthalpy. And here is our formula. So Q equals MCAT. Likewise, Q equals the change in delta H. So delta H equals MCAT. Again, in an endothermic reaction, the delta H is going to be greater than 0 because it is absorbing energy. So pay attention to the sign of delta H. A positive delta H means the system is taking in energy from its surroundings. A negative delta H means that the system is releasing, it's shedding heat. So heat is leaving the system and it's going out into the surroundings. Remember, everything is from the point of view of the system. So we can measure heat changes of a reaction in an aqueous solution in a foam cup calorimeter, similar to the picture I showed you before. We can also perform calorimetry experiments at constant volume with something known as a bomb calorimeter. And that is a more expensive piece of equipment. It's a sealed piece of equipment, and a reaction takes place in this sealed, called bomb, and the heat is released generally from this. Usually this is burned. It's a combustion reactions. The heat of combustion is released into the water, and then all that is calculated with the same formula, MCAT. Bomb calorimeters measure heat release from burning a compound. So here's some examples of fancy and expensive calorimeters, bomb calorimeters. Some things that are easily analyzed in a bomb calorimeter are the caloric contents of foods. That takes us to sample problem number 2. So if we're studying the amount of heat released during a neutralization reaction, which we'll learn about later, we're going to start with 25 milliliters of water with some hydrochloric acid, and we're adding that to 25 milliliters of water containing a base. And you probably already know this intuitively, but acids and bases react. And in this case, they're going to release energy. This is going to be an exothermic reaction. So we're doing this in a foam cup calorimeter. At the beginning, the solution and the calorimeter, everything is at room temperature, 25 degrees. During the reaction, the highest temperature recorded inside the calorimeter is 32 degrees. So what's that? That's a delta T of 7 degrees. Calculate the heat in kilojoules released during this reaction. Assume the densities of the solutions are 1 gram per milliliter. And that's the density of water. And because water here is the solvent for this aqueous reaction. Okay, ACE, analyze, calculate, evaluate, list our knowns and unknowns. All right, what do we know? Well, we know how much HCl solution we have. We know how much NHL solution we have, 25 and 25. We know that the final volume is going to be those two volumes added together. We have our initial temperature, our final temperature. We know the specific heat capacity of water. In this case, since we're looking for kilojoules, we're going to perform our calculation in joules. But we're going to remember that we're still going to have to calculate. We're going to get our answer in joules and then have to calculate that back to kilojoules. And we know our density of the water, which is our solution, is 1 gram per milliliter. So the equation that we know, Q equals MCAT, requires the mass of the water. But we don't know the mass directly, right? But we can find it. We also have to calculate delta T, which we just did. Once we know M and C and delta T, then we just use delta H, the change in enthalpy, equals MCAT to solve for the delta H of this reaction. Well, so the first thing we have to do is get the mass of the water. Well, what do we have? We know we have 50 milliliters of water, and we know that its density is this, so if we multiply mass times density, it's going to give, volume times density is going to give us mass. So now we have the mass of our water, 50 grams. Now we also have our delta T, which we calculated earlier. So now we just plug all these in. Delta H equals MC delta T, plug, chug. We get an answer of 1,500 joules, right around 1,500 joules. And now we need to convert that to kilojoules, so we have a conversion factor. We convert joules to kilojoules, divide our answer by 1,000, we get 1.5 kilojoules. That takes us to thermochemical equations. Yes, math. If a reaction releases heat, we can show that we can show that in the chemical equation by including heat as a product. So this is an exothermic reaction. Here's an example of this. So here is calcium oxide reacting with water. This is something that often happens in heat packs, and it releases heat. And so what we're going to put the heat over here on the product side, because that's something that is produced by this reaction. So we can treat heat like any other reactant. If we have to add heat, we don't have to in this case, but there's some reactions where you have to add heat to the reaction. So if it's an endothermic reaction, you're going to add heat as a reactant. If it's an exothermic reaction, you're going to keep track of heat over here as a product. And this is called a thermochemical equation. It's just like our regular equations in stoichiometry, but we're including enthalpy. We're including the change in heat, the energy released by the reaction. So if it's over here in the product, it's going to be an exothermic. If it's over here on the reactant side, it's going to be an endothermic. So the heat of reaction is the heat change for the equation exactly as it's written, usually as delta H. So we can calculate the heat of reaction. When we do thermochemical equations, there's two rules we have to follow. We have to give the physical state of the reactants and products. As we're going to see later, that matters. And also, the reaction has to be done under standard conditions, which are at 1 atmosphere pressure and 25 degrees Celsius, basically room temperature. And the products and reactants have to be in their usual physical states at that given temperature, 25 degrees. Now, when heat is a product, we can rewrite the equation and pull it out of the product over here as just a plus, and we can just call it a net. We can just say this is what is going to be released by the whole reaction. So remember over here before it was a plus, but now we want to identify it more specifically as something that's being released. This whole reaction releases negative sign heat. It's an exothermic reaction. When heat is a reactant, as in this case, we can also rewrite the reaction. And when we take it out of the reaction, this is baking soda decomposing. We'll take it outside the equation, and we'll just say delta H is positive. That means we had to add heat to the reactant side in order to get this reaction to go. This is different from when we removed heat from this reaction because it was exiting the reaction. So chemistry problems with enthalpy change, delta H, are very similar to stoichiometry problems. You still have to balance the equation, and you have to make sure that the heat released or absorbed is consistent with the number of moles involved in the entire reaction. So not only do you have to balance the moles on both sides of the equation, but we're going to have to keep track of the heat per mole of the reactant involved. So for example, if I had, this is when I have 2 moles of baking soda. Okay, if I had 4 moles of baking soda, that delta H would be double. It would be plus whatever, 258. Oh, here we go, sure. So if 4 is going to require twice as much. What is the heat change for an endothermic reaction? Well, an endothermic reaction, remember, the reactants are going to be at a lower energy state, and they're going to absorb heat, they're going to absorb energy, and move to a higher state. And so the delta H is going to be the difference between your products, which are higher, and your initial starting point, your heat content when you started, which are your reactants. So this is a very common enthalpy diagram, this is known as. And this, when your reactants start low but go high to products, that is you're going to have to add energy to boost these reactants up to these products. And so you're going to have a positive delta H. In an exothermic reaction, it's going to be reversed. The reactants are going to start with a higher initial heat content, and then as they turn into products, they're going to shed that heat, and your delta H is going to be a negative. But again, it's still going to be products minus reactants. Your delta H will always be products minus reactants. And this is an enthalpy diagram just showing your starting level and your ending level. If you're going down, just imagine a ball rolling downhill is going to release energy. Pushing a ball uphill, it's going to require energy. Gravity will help you there. Okay, we mentioned we have to keep track of the physical states of reactants and products in our reactions. Well, why? Well, take a look at these two reactions. Here you have water in a liquid state, decomposing to hydrogen and oxygen, and here you have water in a gaseous state, decomposing. And both of them require an input of energy, so this doesn't happen spontaneously. You have to add energy. We saw this when we did a little electrolysis of water. We had to add energy in the form of a battery to get this electrolysis to happen. But as you can see here, there's a difference of 44 kilojoules between these two reactions. So it matters the starting state of your water. It requires more energy to disassociate liquid water than it requires to disassociate gaseous water. So different states will give you different delta H values, thus we have to keep track of our states. All right, what is the heat of combustion? Well, that's the heat of reaction for the complete burning of 1 mole. We're going to see this a lot. We're going to talk about lots of different heats of different kinds of things. Solution, and vaporization, and fusion. And they're all going to involve 1 mole of a substance. So the heat of combustion is the complete burning of 1 mole of a substance. And here are the delta H's for the combustions. So you burn methane. Again, combustion is something reacting with oxygen, producing carbon dioxide and water. That is a useful definition. It's not fully comprehensive, but it will do. And in each of these cases, we are releasing heat. We're releasing, so we have a negative delta H. But notice, in every one of these cases, we're starting with 1 mole. And even if it requires us to use fractions, that's how we balance this equation. We don't balance this in a normal stoichiometric way. Because what are we doing? We're only burning 1 mole. So we can't transform all of these to make them all whole numbers. If we have to use a fractional amount of oxygen, so be it. So you're going to see this on these 1 mole reactions that we're going to sometimes use fractions, and that's okay. Like heats of reaction, heats of combustion are reported as the enthalpy change at 1 atmosphere, and all the reactants and products have to be in their normal physical states at 25 degrees Celsius. All right, sample problem 3. Using the equation for the reaction above, that's that decomposition of baking soda, calculate the kilojoules of heat required to decompose this much baking soda. All right, so here's our knowns. We have 2.24 moles of baking soda decomposing. This delta H is going to be the delta H of decomposition. That's going to be for 1 mole. But we have 2.24 moles. So what's our delta H going to be? Well, we're going to first write a thermochemical equation. Oh, yeah, you know what? No, that's for the whole reaction. scratch that. This delta H is for the reaction, and the reaction involves 2 moles. Okay. Once we know that this amount here is for 2 moles of baking soda. And so now we're going to take that and say, okay, well, we've got 2.24 moles, and we're going to use this as our conversion factor. Moles cancel, and we're going to get an answer that is slightly bigger than 129. Does that make sense? Yeah, because we have slightly more than 2 moles. We have about 10% more than 2 moles, so our answer should be about 10% more than 129. Makes sense. All right, now let's talk about the heat in changes of state. This is a change in physical state. This does not involve a chemical reaction, but simply the change of state. For example, from water, when it goes from ice and melts, becomes liquid, and it keeps absorbing heat and becomes vapor. We're going to talk about the heats of fusion and solidification. And we've already talked about these fancy words. Fusion just means melting. Is that right? Yeah, melting, and solidification just means freezing. So we talk about the heats associated with something melting, going from a solid to a liquid, and something freezing, going from a liquid to a solid. Now we already talked about an ice cube on a table in a warm room, melts. The ice cube is the system, the table, the warm air are the surroundings. It absorbs heat, begins to melt. But as it melts, the temperature remains at 0 degrees Celsius until all the ice is melted. And this is a little bit surprising. That we see the same thing when water boils. When it's changing a phase, a change in state, whether it's absorbing heat in the case of the ice or shedding heat in the case of freezing, the temperature remains at the freezing point or melting point, which is the same, 0 degrees Celsius, until the process is completed. The water temperature only increases after all the ice has melted. Like ice cubes, all solids absorb heat as they melt to become liquids. And so we define the heat absorbed by 1 mole of a substance melting from a solid to a liquid as the heat of fusion. Just think of it as the heat of melting. All right, and it's the energy it takes to melt 1 mole of something from its solid to liquid form. We abbreviate this as delta H, and then we have a little subscript here for fusion, delta H of fusion. That's the molar heat of fusion to melt 1 mole of something. The heat lost when 1 mole of liquid solidifies, that freezes at a constant temperature, is the molar heat of solidification. It's just the opposite process. That's why they happen at the same temperature, right? Water melts, ice melts at 0 degrees Celsius, and water freezes at 0 degrees Celsius, because the molar heat of solidification is going to be the very same as the molar heat of fusion. Okay, we abbreviate the molar heat of freezing or solidification as delta H solid, becoming a solid. And the heat absorbed by a melting solid is the very same as the heat lost when a liquid solidifies. Again, energy is not created or destroyed. We have to keep track of it. And so there's an absolute equivalence between the heat absorbed by melting and the heat lost or shed when something freezes. So we describe it as like this. The delta H of fusion equals the delta H, the energy lost. So the energy gained for something to melt is equal to the energy lost when something freezes. That's just a mathematical way of describing that. All right, sample problem 4. How many grams of ice at 0 degrees and 1 atmosphere could be melted by the addition of 2.25 kilojoules of heat? All right, so what do we know? We know that we have standard conditions. We are given the delta H of fusion, and we can look that up from a table. And we know the delta H, the energy input into the system is going to be 2.25 kilojoules. So what we don't know is how much ice, what's the mass of ice that input of energy will melt. So we are going to use the chemical equation, water plus this amount of energy, right? 1 mole of this plus this molar delta H of fusion will give us liquid water. So what are our calculations? All right. So we start with this much energy. We know that will change a certain amount of moles. How many? Well, it won't be a whole mole here. It will be 1 mole needs 6 kilojoules, but whatever. So we put this over here, and our conversion factor cancels out our kilojoules and gives us moles of ice. Then we use another conversion factor to cancel out moles of ice and get grams of ice, because that's how many grams are per mole. Now, your answer is going to be what you want, right? Grams of ice that will melt. You crank this through, you find 6.74 grams of ice. This much energy will melt this much ice. Does this make sense? Yeah, because 6 kilojoules will melt 1 mole or 18 grams. This is about a third of this, so it should melt about a third of that, and it does. All right, takes us to heats of vaporization and condensation. So just like we can have heats of melting and freezing, we can have heats of boiling and condensing. When liquids absorb heat at their boiling point, they become vapors or gas. We talked about this last chapter. We call this the vaporization of a liquid. And whether it happens through boiling or evaporation, it is a cooling process. It cools the surroundings. Heat flows from the surroundings into the liquid, whether that's taking it passively from the air in evaporation, or whether it's absorbing it from the flame of your stove. Heat is flowing from the surroundings into the liquid and then allowing that liquid to break the bonds of attraction and go into the gaseous form. So liquid, got to add heat, then we get vapor. We call this the molar heat of vaporization, the amount of heat required to vaporize 1 mole of a given liquid. Okay, you see the pattern here, right? Everything is going to be the molar heat, and it's 1 mole of whatever and the change of state. In this case, the molar heat of vaporization, vaporizing 1 mole of a liquid into a gaseous state. And here are some heats of physical change. This gives us delta H of fusion, that's melting. And remember, freezing is just going to be the negative of that. This gives us the delta H of vaporization. And remember, condensation is just going to be the negative value of that, because it's coming in the opposite direction. Here we're absorbing heat to melt, absorbing heat to boil. Condensing, we would be shedding the same amount of heat, just like we would be shedding the same amount of heat here to freeze. All of these molar heats are derived at standard conditions: 1 atmosphere, reactants and products in their usual physical states at the same temperature, 25 degrees. So the molar heat of the vaporization of water is 40.7 kilojoules per mole. That's a pretty high number, which means it takes 40.7 kilojoules of energy to boil 1 mole of water. And this much energy converts 1 mole of water molecules in their liquid state at standard temperature and pressure to 1 mole of water molecules in the vapor state. And yeah, so here's just basically saying the same thing. All of this can be combined in a single graph known as a phase change graph. And so as temperature increases, and as we add more energy, if we take something like water here, which in this form would be ice. So here's solid water. As we increase the temperature, it will absorb energy, and the temperature will increase and increase and increase until it gets to the melting point, which is also the freezing point, 0 degrees. And then it won't change temperature as it changes phase. Remember, we said this before. Energy either raises temperature or changes phase, but never both. So here it raises the temperature until we get a phase change. Then, once all of the ice has melted, then the liquid can then begin to increase in temperature with an increase of energy until we get to the next phase change, boiling. Then again, water doesn't, and this is at 100 degrees Celsius, and it doesn't get hotter than this until all the water has boiled. After all the water is boiled into steam, then if you keep adding energy, the temperature will continue to climb. So this is a phase change graph, and the key, there's 5 distinct elements in it. You have a solid, where temperature changes, a liquid where temperature changes, a gas form where temperature changes, and 2 phase changes where the temperature does not change, where increased energy only facilitates a phase change. Remember, condensation is the opposite of vaporization. Therefore, the amount of heat released is equal to the amount that was absorbed. So the molar heat of condensation will equal the molar heat of vaporization, just like we saw before with fusion and solidification. Again, another way of looking at the phase diagram with some particle representations. And in each case, we can calculate this with MCAT because it's a change of temperature. But when we calculate this here, we have to use the molar heat of fusion. Again, we can calculate this with MCAT. Then we have to calculate this energy change, this phase change energy by a delta H of vaporization. Then we can go back to MCAT. So on the up parts, we can use MCATs, but we have to use the specific heat appropriate for each physical state, because the specific heat for ice is going to be different from water, and it's going to be different from vapor. So to move something all the way up this phase, all the way up here, from some temperature, say, -20, to another temperature, say, 120, you would have to perform 5 different calculations and then add all the energy levels together. The large values for the molar heat of vaporization and the molar heat of condensation are the reason hot vapors like steam can be so dangerous. You can get a scalding burn from steam when the heat of condensation is released as it touches your skin. That's a massive amount of kilojoules that are released once the steam cools on your skin. It doesn't feel cool, right? But it's cooling by releasing all that heat, and your skin is absorbing all that heat, and it creates a very ugly burn like this. So be careful. Sample problem 5. How much heat in kilojoules is absorbed when this much water at 100 degrees is converted to steam? So we're just simply calculating a phase change here. So what's our mass? What's our molar heat of vaporization? It's this. What are we calculating? Delta H. So remember, we have to add energy to convert liquid to water, and we have to add this much per mole. So our calculation is, we start with our grams of water in liquid state. We know we're going to convert it to moles with our normal molar conversion, and then we're going to take the energy needed per mole to convert it. And then just going to crank it out, 56.1 kilojoules. Does this make sense? Yeah. This isn't quite 1.5 moles of water, so we would expect the answer to be a little less than 1.5 times the molar heat of vaporization to vaporize 1 mole, and that's about right. 1.5 times this would be somewhere around 60, maybe a little less, so that makes sense. All right, what about heats of solution? You can have a heat change when you dissolve something in a solvent. So here is an example of sodium hydroxide dissolving in water. And watch the temperature change against this thermometer. Right? As heat is released, this thermometer is able to detect a change in temperature, which is an effect of that heat being released. He's adding a little more and it keeps going up. The heat change caused by the dissolution of 1 mole of a substance, dissolution means dissolving, is known as the molar heat of solution. Okay, you're getting the point now, right? Delta H of solution. Now the sample problem, how much heat is released when so many moles of sodium hydroxide is dissolved in water? Well, what's our molar heat of solution? Wow, a lot of kilojoules. That's why I raised the temperature so quickly. How many moles do we have dissolved? 2.5. Well, we know that it's going to be, so the total reaction is going to be this times the number of moles. All right, so we're going to start with our moles. We're going to use our conversion factor, this much energy released per mole. Moles are going to cancel, kilojoules are going to be left. Does this make sense? Yeah, 2.5 times that is about that. Calculating heat changes. This takes us to a very important law named after Germain Henri Hess, born in Switzerland, raised in Russia, and he came up with Hess's law, and he decided to call it after the most interesting person he could imagine, himself. And basically the law says whether a reaction occurs in a single step or whether it occurs in multiple steps, the total is the same. The delta H, whether it happens in one step or many steps, is going to be the same. Essentially, if you add 2 or more equations to give you a final equation, then you can add the heats of those individual equations to get the final heat of a reaction. This is known as Hess's law of heat summation. The delta H of the reaction is going to be the sum total of the delta H of the products minus the sum total of the delta H of the reactants. Whether it happens in one step, here's a single pathway, or whether it happens in multiple steps. The difference between this and this is the same. Whether you jump down once or you jump up and down and up and down and up and down, at the end of the day, you've come down the same amount. You've shed or released the same amount of energy, because this would be an exothermic reaction. So just like this hill, right? If there's different paths to the top of this hill, whether you take a direct path or whether you take an indirect path, at the end of the day, you still have changed the same amount of altitude. Maybe you've taken more steps, but your altitude change from here to here is the same. That's basically Hess's law. So let's say we wanted to find the enthalpy for the conversion of diamond to graphite. But this happens to be a reaction that happens so slowly that we can't measure it directly. But we can find it by using the following combustion reactions. So we can use the combustion reactor, the combustion of graphite with oxygen to carbon dioxide, and the combustion of diamond to carbon dioxide. And we can figure out what are we trying to find here? We're trying to find the conversion of diamond to graphite. So we don't have one that goes direct, but here's what we're going to see. We can add these equations together. So the first thing we'll do is we'll take this first reaction and we'll flip it, because we want to put graphite over here as a product. Now when we flip a reaction, it's going to flip the delta H, just because we're doing the exact opposite. So if running it one way was exothermic, then the next way is going to be endothermic. And that's what we see here. We go from an exothermic reaction to an endothermic reaction. We leave this reaction the same. Now look what we have here. We have carbon dioxide on this side and this side. We have oxygen on this side and this side. And whenever you have something, if you have something both on both the product side, the reactant side and the product side, when you add these reactions together, these cancel. Likewise, if you have the same things, this is like a reaction. If I have like 10 on this side and this is a 10, I can subtract 10 from both sides and leave everything else still equal. Well, carbon dioxide on this side, carbon dioxide on this side, it will cancel. This will cancel, this will cancel. So this gives us this. We end up, when we combine these reactions, we get diamond breaking down into graphite. And since we did, instead of doing that in steps, we just add this as the sum of all the steps. And we see that the delta H is very slightly exothermic. So even though we can't see this reaction directly, we can calculate the energy change because this would be one of the intermediate steps if it were to take it. So the first thing we looked at is this thing just dropping all the way down. Then we looked at this thing dropping all the way down. And then we realized that if you reverse one of these reactions, you can find the difference between these two drops all the way down, and that is the delta H of something just dropping this far from diamond to graphite. So this is a very practical use of Hess's law to find something that you couldn't find normally, or at least directly. What if we wanted to find the enthalpy change for the formation of carbon monoxide from its elements? Well, it's easy to write this reaction. Carbon plus half an oxygen. Again, the reason for this is being half and not being balanced out is because a formation reaction creates 1 mole, right? So what would the delta H of creating 1 mole of this be? Well, we can't do this in the lab because every time we react graphite with oxygen, it wants to turn into carbon dioxide. So we produce a lot more carbon dioxide rather than our target molecule, which is carbon monoxide. But can we do this with a Hess's law? Sure. Because there are 2 reactions that we can carry out in the lab that, when added together, will give us this reaction that we can't carry out in the lab. So here we are. So we're going to take the combustion of graphite to carbon dioxide and the combustion of carbon monoxide to carbon dioxide, and we're going to manipulate these, add them together, and find out what we're looking for. So again, what are we looking for? What's our goal reaction? We want to end up with carbon dioxide. So we're going to take this reaction here and we're going to flip it because we need carbon dioxide over here as a product. That's going to put carbon dioxide over here, which will cancel with this. It'll put this over here on this side, which will partially cancel with this, you'll see. So we flip this bottom reaction, which flips our delta H. And now we combine these reactions together. And what do we see? The carbon dioxides cancel. We have a half of an oxygen over here and a whole oxygen over here. So this will cancel half of this whole oxygen and leave us a half of an oxygen over here. We add all this together and boom, what do we get? This is the reaction we're looking for. Carbon plus oxygen giving us carbon monoxide. What will the delta H of that be? Just add these together and this will be this reaction. We can't observe this directly in the lab, but we know this is what would happen if we could. Again, here's the stepwise breakdown. This takes us to standard heats of formation. What are some cases where it might be hard to measure the heat change of a reaction? Well, what if you didn't have the materials? Or in the case of diamond, where the reaction was too slow to measure, or the chemicals you're talking about are explosive, or they're deadly, or they're too expensive. Well, then we can still calculate the heats of reaction from something called the standard heats of formation. Again, like everything else, the standard heat of formation, abbreviated this way, of a compound is the change in enthalpy to form 1 mole of a compound from its elements in their standard states at standard conditions. Now, the delta H of formation of a free element that is already in its standard state is 0. Nothing. Why? Well, it takes no energy to form a free element that's already in its standard state. If you're already sitting in a chair in the classroom, how much energy does it take you to sit in a chair in the classroom? None. You're already there. So these elements are already in their standard state. They require no extra energy to be what they already are. So the energy it takes to form them is 0. So this will include all of your diatomic molecules, as well as a couple of others. Carbon in the form of graphite is 0. That's its natural state at room temperature. So the delta H of formation of elements already in their free state and standard condition it's going to be 0. So here is a table of standard heats of formation, again, standard conditions. And as you'll see, things that are already, iron is a solid at that temperature, its heat of formation is 0. Here are your diatomics, 0. Here is oxygen, 0. But everything else is going to, so it's not already in its natural state. We just saw where it takes a little bit of energy to transform diamond to graphite, but graphite is that's already there. It's free in natural state. So the heat of reaction becomes the difference between the heats of formation of all the reactants and all the products. So this is a reaction that maybe we can't observe directly, but we can calculate it by saying, well, look, what would it take? How much energy would it take to make all the products? And let's subtract all the energy it would take to make all the reactants. And whatever that difference is, that's the delta H of your entire reaction. The difference between all the enthalpy of the products minus all the enthalpy of the reactants. So here's another sample problem. What's the standard heat of reaction for the reaction of gaseous carbon monoxide with oxygen to form carbon dioxide? All right. Here's what we know. We have the heat of formation of a bunch of these things. What we don't know is the heat of the entire reaction. So the first thing you're going to do is balance the reaction between these two, carbon plus O2 yielding CO2. And then we're going to find the delta H of the reaction by using these heats of formation. So here's what it will look like. We'll write the balanced equation. 2CO plus O2 is that. And then we're going to say, hey, what does it take to make all of these reactants? Okay, let's look at this one. How much does it take to make oxygen that's already in its standard gaseous state at standard temperature? 0. Great. How much does it take to form carbon monoxide? Well, we go back to we have that carbon monoxide. It's going to be this per mole. Well, we have 2 of those, so we're going to multiply that by 2, and that's going to give us this many kilojoules to make our reactants, because this was a 0 and this is a negative 221. Okay, then we're going to find the product in the same way. We're going to say, what does it take to make CO2? Go back to our table. Making CO2, okay, is this much, cost it that much to make, but that's per mole. How many moles do we have? We have 2 moles, so we do it by this mole conversion, and we get this is the total. And so now we have this is the energy it takes to make all the reactants, including one that was 0, and this is the energy it takes to make all the products. And now we're just going to subtract them. We're going to subtract the products, or take the products and subtract the reactants. Products minus reactants, keep track of your signs, and the delta H of this entire reaction is this amount. Thanks for your time and attention.